Hi everyone, welcome back to my channel. My name is Jeffrey. Today we're going to talk about signal transduction. Now this lecture is going to be very dense. A lot of these pathways have to deal with the G protein coupled receptor. So I'm just going to give you guys a very brief rundown of what a GPCR is, or G protein coupled receptor is. Okay, it's going to have essentially 7 transmembrane channels. It's going to have that receptor on the extracellular side, and it's going to have a G protein, as the name suggests, on the intracellular side. Okay, and essentially what happens is that your G proteins segregated into 3 subunits. It's going to be the alpha, the beta, and the gamma subunits. So now when you have a ligand that's specific for this GPCR, it binds to its receptor. What happens is you have your GDP that's bound to your alpha subunit. It's actually going to turn into a GTP. And as a result, you're going to have these subunits dissociate, and you're going to have your beta and gamma subunits dissociate from your alpha subunit, which is now bound with GTP, which means it's active, and as a result, it's going to phosphorylate some downstream effectors, okay? And after a while, obviously, you want to stop this signal. You're going to have an enzyme. It's going to be called phosphodiesterase, and what it's going to do is it's going to make that GTP go back into a GDP. And keep in mind that once the alpha subunit is attached to a GDP, it is inactive again. So it goes back with its beta and gamma subunits, forming that G protein, the inactive G protein that we were talking about before. Okay, so that's essentially a brief rundown of signal transduction. Let's move right into the beta adrenergic receptor pathway. So there's going to be 2 beta pathways, and it's going to be beta 1, beta 2. You're going to have beta 1 is in your cardiac muscles, and beta 2 is going to be in your smooth muscles. And the way I remember this is, number 1, the thing that you cannot live without is your heart. So obviously beta 1 is going to be in your heart. Now, regardless of the type of receptor, it's going to have the same downstream effect. So remember, the ligand is going to bind, your G alpha subunit is going to disassociate, and it's going to have basically an increase in adenylyl cyclase activity. And adenylyl cyclase is going to actually activate this thing called protein kinase A. So it's going to increase pKa activity, and as a result, that pKa is going to make cyclic AMP. And cyclic AMP is going to have a lot of downstream effectors, and that's the entire reason why we call this signal transduction, because one signal is leading to a multitude of effectors. Now, one of those effectors I wanted to talk about was just, cyclic AMP can activate CREB. CREB is a transcription factor, and as a transcription factor, it increases the transcriptional levels of certain genes, okay? And as a result, you're going to have increased expression of certain genes, all right? And now the beta adrenergic pathway is going to be a GS pathway, okay? So beta is GS, doesn't matter whichever type of beta it is. And then for your alpha 1 adrenergic receptors, this is actually going to be a GQ pathway, and your alpha 2 is going to actually be your GI pathway. Now, the way I try to remember this is beta is going to be associated with your GS, right? And alpha is always going to be before beta. So beta is secondary to alpha. Now, GI is going to be the pathway that is directly inhibiting the GS pathway, so it's directly against it. So as alpha 2, it's going to be secondary to alpha 1, right? So just beta and 2. I try to correlate those two things together. It might work for you, it might not, but that's just the way I kind of think about it to help me remember it. Now moving on, so the GQ pathway, it's actually, what's going to happen is the ligand binds. So you have your ligand binding to the receptor, the G alpha subunit disassociates, and as a result, it's going to activate phospholipase C, okay, PLC. Phospholipase C, when activated, is actually going to dissociate. It's going to dissociate into 2 units. One is IP3, the other is diacylglycerol, which is DAG, and DAG is going to activate your protein kinase C. So remember, before we were talking about protein kinase A, this one's actually going to be protein kinase C. Protein kinase C is going to have a lot of downstream effectors. IP3 is going to trigger the intracellular, extracellular calcium coming intracellularly. So you're going to have an increase in intracellular calcium levels. Calcium in a lot of cells do a lot of crazy things, so they also have a lot of downstream effectors. So you can see how one signal can really lead to a multitude of downstream effects in a cell, okay? And then for alpha-2, your GI, essentially it's going to be the exact same thing, just opposite for your GS pathway. You're going to have your ligand bind. It's actually going to decrease the amount of adenylyl cyclase activity, and as a result, you're obviously going to have decreased levels of pKa, and as a result, you're going to have decreased levels of cyclic AMP, and because cyclic AMP cannot affect those downstream effectors, now you're going to have less of an effect from before. Okay, it's going to inhibit a lot of pathways. Moving on to the cholinergic muscarinic receptors, these are going to be your acetylcholine, and acetylcholine is going to it's going to bind to its receptor. And as it binds to the ligand, it's a ligand-gated ion channel. So it's a ligand-gated ion channel. And when acetylcholine binds to it, it's going to trigger the release of calcium into the cell. So it's going to kind of have that same effect as your IP3, but it's going to be a direct effect. It's going to directly open up those channels on the cell membrane, and it's going to trigger the release of calcium. And as we said before, calcium actually can lead to many different effects inside of the cell. Insulin, when insulin binds to its receptor, it's actually going to increase receptor tyrosine kinase activities. Receptor tyrosine kinases do a multitude of different effects, one of which can be, for example, the increasing transcriptional levels. So it can act, it can act downstream as a transcriptional factor, and increase transcription of certain genes. We often like to think of insulin as one of those things where you have high blood sugar, and when you have high glucose levels in your blood, you want to bring them in. So when you have insulin, part of one of those downstream effectors is the increase of GLUT receptors. And when you have that increase of GLUT receptors, you're going to have increased glucose inside of the cell, and you take it out of your bloodstream. Right, glucagon is going to be the converse of that. It's when you have low blood glucose levels, and when you have low blood glucose levels, you're going to trigger the release of glucagon. Glucagon is going to actually bind to its receptor. It's going to be actually very similar to your GS pathway or your beta pathway, right? So your ligand is going to bind. It's actually going to activate adenylyl cyclase. And as adenylyl cyclase gets activated, it activates pKa. pKa activates cyclic AMP, and you're going to have many of the downstream effects that you would have from that GS pathway. Okay, so then for steroids are a special molecule because keep in mind that they're actually nonpolar for the most part. So they can actually diffuse through the cell membrane, the plasma membrane, and they can bind to certain cytoplasmic factors in the cytoplasm and actually translocate into the nucleus, affecting transcription and translation, and serve as transcription factors. Okay, and that's just going to lead to the increased amounts of protein, but it's actually going to be the time that it takes to actually have an effect is going to be longer than your G protein coupled receptors. And the reason for that is because translation takes a long time compared to just having an immediate downstream effect. Now for your no receptors, you're actually, there's going to be two things here. It's actually going to be your NO nitric oxide, and you're actually also going to have this thing called atrial natriuretic factors. So these two things, what they actually do is they're going to directly bind to this receptor called a guanylyl cyclase. And as a result, that's actually going to be kind of like your adenylyl cyclase, but in this case, it's going to increase your cyclic GMP levels. And your cyclic GMP acts as a secondary messenger, and it affects many different things downstream. Okay, and then for your toxins, there are two toxins that are really important. It's cholera and pertussis. So the way I try to remember this, for cholera, just remember cholera causes gas. Gas stands for G-alpha S, which stands for the inhibition of these pathways, okay, or overstimulation, okay, of these pathways. Essentially, what these two toxins do is they do ADP ribosylation. So you're just going to continuously, and that just leads to continuous stimulation of those pathways, because now remember that those pathways, they need to have their GTP transferred back into a GDP, and to be inactivated, right? So now you're just going to have continuous stimulation. Now, pertussis is actually going to be your GIS, so it's going to be your inhibitory pathways. So that's going to be continuous stimulation of an inhibitory pathway, which leads to increased, how do you say it? Increased inhibition, if you will. All right. So I hope that this video has been helpful. I hope that we covered a lot of different things and maybe cleared things up a lot for you guys in terms of your beta, your alpha-1, and your alpha-2 adrenergic receptors.